Okay. So we will record this class today for that purpose. So back to the section on capacitors and dielectrics, just a little recap. So we create a capacitor by putting charge on opposing plates that are kind of facing each other. We call this a parallel plate capacitor. And here you can see what it looks like more practically when we kind of roll it up. They even have a way of just rolling up one piece of metal with one piece of dielectric. So the dielectric for most capacitors is actually really simple. It's just a piece of paper usually. But you can use all kinds of things to get different sizes of capacitors. And of course, the physical size of the capacitor also plays a role, because the area of the plates means that you can fit more charges on. Bigger areas, more charges; smaller areas, fewer charges. And then the distance between the plates turns out to matter, because if you bring the plates closer together, then it turns out that you can actually put more charges on it. Actually, more charges attract each other that way, so that more charges want to be on the plates. But it gets to a point that there's this trade-off between, if you get more and more charges on there, you get this huge, bigger and bigger electric field. So eventually the force on the charges from the other charges on the other plate becomes so strong that the charges can actually jump across. And once the charges jump across, then it's no longer, a capacitor so much as it is just like a wire. You just get this lightning striking across, and it's just like you've connected the two plates in some way. So you get a little bit of a trade-off there, but you can actually fix that trade-off by adding a dielectric. If the electric field gets too strong so that the charges start to jump across, you can put a piece of rubber or a piece of plastic or a piece of paper or something that's not conductive in between here, which will actually reduce the electric field for that amount of charge. And then you can put more charges on it, and they won't jump across, and make it bigger. And we learned that we created a definition for the capacitance of a capacitor equaling the charge over the potential. So that's essentially the amount of charge you can fit on the capacitor divided by the potential energies of the charges that are on the capacitor per unit charge. So that's the definition of the capacitor, of the capacitance rather. And capacitance is measured in farads, which is capacitance, charge per voltage, or coulombs per volts. And we name it after Faraday. And then we looked at the geometry of the parallel plate capacitor, and we were able to derive an equation that tells us, or a formula that tells us the capacitance according to the geometry, which is the area of the plates divided by the distance between the two plates. And turns out that there is a factor that you have to put in there to make it an equation, and that turns out to be the permittivity of free space, which we also saw when we were calculating the force on charges with Coulomb's law. So that turns out to be a very important number in the electrical world, actually in just the physics world in general. And then we also learned that when you put a dielectric in between the plates, that the capacitance changes by this thing we call the dielectric constant. And the dielectric constant is essentially a ratio of how much it increases compared to a capacitor that has nothing in between the plates, like a vacuum. So when you have nothing in between the plates, your dielectric constant is 1. And as for different dielectrics, it increases as that ability to store charge increases. All right, then there's also this quick way to calculate the electric field in between the two plates of a capacitor. If you know the voltage across the plates and you know the distance between the plates, then you can calculate the electric field between the two plates. But that's only true for air-filled capacitors. If you want to do that for one if you want to use that same equation, if you want to do this for one that has a dielectric in it, I think you have to divide on the right side by the dielectric constant. I believe that's the case. They don't do that here, but I think that's how you do it. Let me just think about it just for a second. Yes, you would divide by the constant. So you divide by, if you want to divide by kappa, which is this dielectric constant right here, and you wanted to know the electric field, you would have a divided by kappa here. So when you calculate the electric field, it would be kappa times voltage divided by distance between the plates. So anyway, those are just, that's just a quick review of those things. And then they talked about a little bit about how the dielectric works, which I also talked about by polarization and the rotating of charges, you could think of it as. Now let's talk about what happens when we use these things inside of a circuit in a real kind of world situation. So the first thing that we're going to do is we're going to hook these up to a battery, and we're going to hook up 3 separate capacitors, one right after the other. So here we have capacitor 1, which we've connected to the positive side of this battery. And then on the negative side of that capacitor, we've connected it to the next capacitor. And then we've connected it to the next capacitor. And then we connected it to the next capacitor, you know, and just boom, 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 right after the other. What happens in this case is that, well, I'm going to do it a little bit differently than they do it, but let me get my drawing tools out here. What's happening in this case is this battery is putting a certain amount of charge, positive Q, on this side of this capacitor. And that's going to attract a certain amount of negative charge from this side. In reality, what's happening is that it's putting negative charge on this side of this capacitor, and that is going to repel negative charge on this side, leaving you with positive charge here. And then that repelled charge goes to this other capacitor through this wire, so it ends up here. And that repels a negative amount of charge from this side, leaving a positive charge here. That negative charge that's repelled goes to this side. I mean, it literally happens from the negative side because the negative charges are the ones that are moving. But in any case, you end up with a negative amount of charge, negative Q here, and then that negative charge repels an equal amount of negative charge from this side of this capacitor as it kind of cascades through all these capacitors, and that ends up going down into the battery, right? So each one of these capacitors has the same amount of charge on each side. Negative Q, positive Q, negative Q, positive Q, negative Q, positive Q. The result of that is that you have a capacitor, a capacitance that is equivalent to one single capacitor that has the same amount of charge on each side, but it has a much bigger distance between it. It's kind of like we've added the distances between these 3 capacitors together. So now I have a capacitor that has the same amount of charge as each one of these has, but a much bigger distance between them. Well, we already know that if you have a bigger distance between the plates, you have a lower capacitance. So the result in putting capacitors one after the other, which we call in series when we put them one after the other, the result is the capacitance goes down. So if you have 3 capacitors that all have particular amount of capacitance, let's say that this one has a capacitance of 1 farad, and this one has 2 farads, which of course these would be three huge capacitors. Let's say this one's 3 farads. Then you put them all together in series like this. The overall capacitance here will actually be less than the smallest capacitor here. So this capacitance will be less than 1 farad, the total capacitance of the combined added together. And in fact, we can actually figure out what it's going to be because we know that, let's see, do they do that here? Yeah, here we go. We know that the capacitance for a capacitor is equal to Q over V. And we know that the Q on each of these capacitors is the same. So if we solve this equation for the voltage, we get voltage equals Q over C. And we get that the voltage of the first capacitance is Q over C1. For the second capacitance, it's Q over C2. And for the third one, it's Q over C3. Also, voltages that are in series add together. So the voltage across this one plus the voltage across this one plus the voltage across this one is equal to the voltage all the way across it, which is equal to the voltage across the battery, because voltage from here to here is connected to the battery, right? So we have the voltage across the battery equals the voltage across the first capacitance plus the voltage across the second plus the voltage across the third. And we know what those voltages are from our equations about voltage and capacitance. It's Q over C1, Q over C2 plus Q over C3. So we get this equation. Q over C1 plus Q over C2 plus Q over C3 equals the voltage across the entire group of capacitors, which is the Q over the capacitance of the combined series capacitance. So we call that capacitance series. That's like this. That's the voltage across this capacitor, which is the three combined in series. That imaginary capacitance that we've created. So if this is true, guess what? The Q's are the same in all of these, so we can actually remove the Q. We can just divide by Q on each side of this equation, and we get this equation. Why would we do this? Well, we do this because when you do have capacitors in series, you want to figure out a quick way to calculate the combined capacitance of those. Instead of trying to treat them like separate capacitors, you treat them as one. So this is the one capacitor that is equivalent to multiple capacitors in series, and you can do as many as you want, it turns out. If they're all connected in line, one after the other, after the other, after the other, then they're considered in series. There is one caveat. They're not considered to be in series necessarily if you do something like this. You have some branch that goes off connecting to something else. They have to be in series, one after the other, without anything breaking off, without anything branching off over here. So that's one of the definitions of being in series. So we can calculate the capacitance of any number of capacitors in series, the total overall capacitance of any number of capacitors that are wired up in series, just by using this formula. 1 over the capacitance in series equals 1 over the first capacitance plus 1 over the second capacitance. One of the things that people forget to do is that they'll plug in their capacitances into this and get a number and then use that as the capacitance in series, but that's not true. You still have to take 1 over that number to get the capacitance in series. You have to invert that number in the end. So let's do an example here. We have 3 capacitors that we're going to line up in series, 1 microfarad, 5 microfarads, 8 microfarads. And then we want to know what is the total capacitance of that. Well, we plug them into the formula, 1 over 1, 1 over 5, 1 over 8, and we get the answer 1.325 over microfarads, because the microfarads is in the bottom here. So if you add these 3 fractions together, 1 over 1 plus 1 over 5 plus 1 over 8, you get this number, 1.325. And then you, but that's not your answer, because that's over microfarads. We need to invert that. So we take 1 over 3.25, 1.325, and we get 0.755 microfarads. That is the total capacitance of those 3 lined up in series. Now you can check your answer pretty quickly to see if you've got it right, see if you finished the problem. This number right here, 1.325, is not smaller than the smallest capacitance. And we already demonstrated that it has to be, or we said that it has to be. This demonstrates that it has to be. So if your number is not smaller than your smallest in-series capacitor, you know that you've forgotten probably to take 1 over the answer to get the actual answer. Here's an interesting one where you have, let's see. Here they're doing 40. Oh, here they're showing why this always ends up being smaller than the smallest one. This is actually an even better demonstration. So instead of writing 1/1 microfarad, they write 40/40 microfarads, and then 8/40, and then 5/40. These are the same numbers as up here, right? 40/40 is still 1, and 8/40 is still 1/5, and 5/40 is still 1/8. But here it kind of shows that you're getting a 50. This is like adding 53 of these things together, 53 40 microfarad capacitors together, or something like this. And the number always ends up being less than, right, the smallest one. And the smallest one was 40/40, and your answer ends up being 40/53. It ends up being your smallest one over the sum of all of these put together. So that's kind of a proof that that is always going to be the case. You can think of it as. However, it's different if we line them up in a different way. What if we connect all of these capacitors on one side to one side of the battery? So we've connected the tops of the capacitors to one side and the bottoms of the capacitors to the other. In other words, this is kind of like connecting each of these capacitors together on the top and each of them together on the bottom, and then connecting them to the battery. I like to draw it that way sometimes just because it illustrates it a little differently, makes it a little, make just a different configuration, just so people can see it differently. So now I have these three capacitors, and I'm just going to connect them together like this on the top, and I'm going to connect them together on the bottom. So I've wired the tops and bottoms together, and then I take a wire from one of these wires and connect it to one side of the battery, and another wire and connect it to the other side of the battery. Well, this is what we call connecting capacitors in parallel. All one sides are all connected to one side, all the other sides are connected to the other side. And you can see why we call them connected in parallel, because if you draw them out like this, they actually end up with these parallel lines going down, right? When they're connected in parallel, it's kind of like making one capacitor where we've increased the size of the plates. Instead of increasing the distance between the capacitors, we've increased the size of the plates. So the plates get bigger. And we know that when the plates get bigger, the capacitors get bigger. And it turns out to be a very simple calculation to calculate the overall capacitance. Capacitors in parallel, you just add the capacitances together and you get a bigger capacitor. And that's because all you're really doing is increasing the amount of charge you can store on each side. You're taking the charge that you can put on this side and adding it to the charge and adding it to the charge, and you're doing the same thing on the negative side. So it's just the capacitance is adding together. It's quite simple. Capacitors in parallel, you just add them together. If you have that 1 microfarad, 5 microfarad, 8 microfarad capacitor, and you put them in parallel, you're just creating a 14 microfarad capacitor, because that's 1 plus 5 plus 8. Quite simple. And you can do it ad nauseum, however many you want to add together. What happens if you have a circuit like this? So we have a circuit where we have a branch coming in, and that branches off into two different branches. So we have a wire coming in, branching off to two different branches. In one of these branches, we have these two capacitors. In one of these branches, we have this one capacitor. Now, which one of these has some capacitors in series? Which branch has capacitors in series, the left or the right?
The left, right?
The left, right? Oh, just kidding.
No. Yeah.
The left one, correct? Okay, so the left one has two capacitors that are one right after the other connected, and there's nothing branching off in between. So these are in series. So we can use our equation for series capacitors to create a capacitor that would replace these two. And we use that, and we replace those two that are in series with the equivalent capacitance in series. And then we have two capacitors in parallel, right? So then we can replace these two capacitors just by adding them together, capacitor in series plus capacitors, plus the capacitor 3, which was in parallel with the capacitor in series. So we've reduced it down to one capacitor that is equivalent to 3 capacitors. So how did we do it? if we do this particular example with capacitor 1 equals 1, capacitor 2 equals 5, capacitor 3 equals 8, then we have to calculate the capacitance in series, the equivalent capacitance in series for capacitors 1 and 2, 1 and 5, which are 1 microfarad and 5 microfarads. So that's 1 over capacitor in series equals 1 over capacitor 1 plus 1 over capacitor 2. Plug in the 1 over 1, 1 over 5, get 1.2 over microfarads. Remember, you have to invert that, and you get your answer, capacitor in series, or capacitor S, equals 0.833 microfarads. Then the total capacitance was that capacitance in series plus capacitance. That's not correct. That's a typo. That should be capacitor 3, right? And the equivalent capacitance in series we just calculated is 0.833, and capacitor 3 is 8 microfarads. So we add those together to get our total capacitance of, or our overall capacitance of that set of capacitors. We do this in electronics for a couple of different reasons. Sometimes we need a specific capacitance. Maybe this is the capacitance we need, but we don't have a capacitor that's exactly that. But we do have these capacitors, 1 and 5 and 8. So we can put them together to make this capacitance. Sometimes we're just combining electronics that we already have, plugging one thing into another, for example, and we need to know what that overall capacitance is to understand the performance of the electronics that we've created from putting those together. So sometimes we do it on purpose to make a specific capacitance. Sometimes we have to know the capacitance of things that already have a particular capacitance that we can't change. And so either way, it's useful to know how to do this. Oh yeah, here they actually show a, oh, this is a calculator. So here they're showing the capacitors in a calculator. Here are some capacitors, here are some capacitors. I don't know if that's capacitors or not. These things might be capacitors as well. Those probably are. But one of the reasons that they use capacitors is to provide energy for storing memory. For example, on your cell phone, if your battery runs out, if your battery dies, one of the things that the capacitors in your cell phone can do is preserve some of the things like the time stamp on the cell phone. It's not as big a deal in cell phones anymore because cell phones use flash memory, and flash memory is not erased when the cell phone dies. So when the battery goes dead, flash memory stays in the microchip. Flash memory is essentially a microchip type thing that stores memory, stores information. But it used to be that when you had like cell phones from even 7 years ago, sometimes had memory that got erased if the battery went dead. So you'd have to have a way to keep power to your memory, and that's what they're doing here. They store electricity, or they store electrical energy in the capacitor, and that capacitor releases that energy while the battery is off, or while the thing is off, to save that memory. So that's one way that it's used, and it's not used as much that way anymore, which is nice, because then your batteries don't have to be charging capacitors all the time. But it's always the case that capacitors are used to store energy, no matter what that energy is used for. And it turns out that the energy stored in a capacitor is equal to the charge in the capacitor times the voltage, because voltage is energy per unit charge. So if you multiply by the charge in the capacitor, and then multiply by the voltage, then you get that. But it's also divided by 2. And the reason it's divided by 2 is because the capacitor, the charging process of the capacitor is pretty much a linear thing. And so so when it's first charging energy, it when it's first charging the capacitor, it's putting on just a little bit of energy at a time. Towards the end, it's storing a much larger amount per time. But the average over time you get by dividing by 2, by taking the initial plus the final and dividing by 2. So it's just a basic kind of statistics thing. There's more to it if you're thinking in terms of physics, but it still comes out the same way. So if you know the charge, you know the voltage, you divide by 2, then you can calculate the energy stored on a capacitor. We also know that Q is equal to capacitance times voltage. So if we replace Q up here with capacity times voltage, with capacitance times voltage, then we get a couple of different equations. Or if we replace V with Q over C. So you can do charge times voltage over 2, or you can do capacitance times voltage squared over 2, or you can do charge squared over 2 times capacitance. So of the 3 things that we know about capacitors, charge, capacitance, and voltage, if you know any 2 of those 3, you can calculate the energy stored in the capacitor just using one of these 3 equations. So this is a good thing to remember, the energy stored in the capacitor, 3 different ways to calculate it. QV over 2, CV squared over 2, or Q squared over 2C. Right there. So here's an example, an external defibrillator. When your heart fibrillates, it means that it skips a beat or stops beating or does something funky. And that's not good for your body. It usually results in really a regular heartbeat or a very faint heartbeat or a very slow heartbeat, or it just stops altogether. Your heart just stops. You don't want that to happen. None of those things are good for your body. So what they developed is this automatic external defibrillator to defibrillate your heart. When you defibrillate the heart, what you want to do is you want to create electrical pulses that cause the heart to contract at the right time, at the right amount, and re-regulate the heartbeat. In some cases, that means just start the heart. In other cases, it means kind of maintain the heartbeat or fix the way it's beating to make it right. But it's a thing that essentially monitors your heart and then adds shocks to your body to make the heart beat properly. Those shocks come from capacitors because they have to be a fairly quick and fairly big shock to make it work. If you've ever seen somebody use a defibrillator in a movie, they say clear because they don't want anybody else to be touching the person's body except for the defibrillator. And the person holding the defibrillator pads is insulated from the shock by the handles. But you don't want to be touching that body because that shock can go into you. And when they actually administer the shock, the whole body convulses. And the reason the body convulses is because the muscles, all the muscles, not just the heart muscles, might start contracting if you're putting a big enough charge. Like to start the heart, it's a big enough charge that many of the muscles in the body will contract, including your back muscles, which makes your back arch so your body comes up off the ground, and your hands will clench and your arms will even bend up towards your body sometimes because of your biceps clenching, and your feet, your toes will actually your toes will curl so that your feet curl up into kind of like this claws kind of thing, and your legs might even like pull up towards your body. All of that will happen at once as soon as they shock you because all of your muscles will be engaged, not just your heart muscle. Not a very pleasant experience for the one receiving the shock, and usually results in a fair amount of aching muscles at the end. But anyway, the point being is that here is the amount of energy that that is going to be delivered in this particular example, 4 times 10 to the 2 joules of energy. And so that's 400 joules. And that's the amount of energy that's going to discharge from this capacitor. The capacitor is initially at 10,000 volts, 1 times 10 to the 4th volts. And we want to know what is the capacitance. So they've told us the energy and they've told us the voltage. Well, there's one of those equations for energy of a capacitor that has capacitance, voltage, and energy in the equation. E equals CV squared over 2. We're going to solve it for the capacitance, and we're going to get 2 times the energy in the capacitor divided by voltage squared. We plug in our numbers and we get 8 microfarads. turns out not a very big capacitor, actually. It's not actually, it's not actually a big number. It's microfarads, right? However, the amount of charge that this thing is going to deliver can be quite large and will be quite large. It'll actually pump a fair amount of charge into the body. And that is actually evident from the voltage here. The voltage here is quite large, even though the capacitance is small. The voltage being large suggests that the charge would actually have to be a fair amount of charge. And that takes us to the end of the chapter. So we do have a couple of minutes. If anybody has a question from one of the problems from in the homework, does anybody have a question from the homework you'd like to ask?
Number 2.
A question
on
on
number 2.
Okay, let's take a look at number 2. That's not the right class. There we go. Okay, so here we have our parallel plate capacitor, positive and negative charge plates separated by a distance d. They've told us the potential across here. So the potential that's our voltage, right? And they want to know position of the the electric potential and electric field at different locations between 0 and D. Okay, so they want to know what's the electric potential at different positions and the electric field at different positions. Okay, and then they're going to move a charge along through here, right? So all of this comes from the very beginning of the part where we talk about capacitors. If we go back to the book and we look at the first section on capacitors, it goes back to maybe 19.5. So one of the things here, one of the equations that might be useful to us that we might remember is that the voltage or the potential equals electric field times distance. And so that might be useful to us just as a thing. Let's go back one more section and see if we can find, because I'm remembering let's see. I think I'm remembering an example that was going to be helpful to us. I'm just trying to remember where it was. It might have been here at the very beginning. Yeah, here we go. So this is kind of like a parallel plate capacitor, right? Where we have, and this is where they're first defining what these things are. So maybe this might be useful because they're actually talking about how potential is defined between two plates. So how the electric field is defined between two plates. It's not the one that has the example I'm looking for. This one probably is though. So here we actually put a charge between two plates. So it's like in a capacitor, right? And they talk about the electric field and the relationship between the voltage and the electric field and distance here. And they also talk about Um, let's see. Yeah, right here. So this one is actually kind of interesting because they're actually talking about here the electric field between two parallel plates, and they tell us that it ends up being the same everywhere. The electric field is uniform between these two plates. And so how can we calculate it? We can actually calculate it by using the voltage between the two plates and dividing by the distance, which is shown, you can show it right here in this equation. The electric field, if it's a uniform field, and it is between these two plates, because they do talk about why that is here, but it's a uniform field, and so you can calculate it by taking the voltage between the two plates and dividing by the distance between the two plates. And that isn't that the first part of the question? Let's go find the question really quick. Where'd the question go? Right here. So, yeah, question 2. So what is the electric potential and electric field at different locations? So if the electric field is uniform, then all we need to know is the voltage from plate 1 to plate 2, which they give us, and the distance between them, 0.480. And that's the electric field everywhere. So it doesn't change at all. So we calculate that. 1600 volts divided by 0.480, and it's the same here, here, and here. Electric field. It's always the same all the way across. In my particular case, it's negative 3.33, negative 3.33, negative 3.33. And why do I know it's negative? Because it points from the positive plate to the negative plate, and this is the positive x direction. So that's negative direction for this field. So it's negative 3.3, oh, not 3.33, 3,333. So that's 1600 divided by 0.480 is negative, is 3,333. That's that number. For you, it will be different. But how do we calculate the voltage at different points? Well, also at that same place in the book, they do this for us. They say, oh, look, the voltage is equal to the electric field times the distance, but we're going to go at different distances. So it's not just the voltage across the whole thing. We're going to look at it at different distances. So we go back to our homework. There it is. So they want to know the voltage at 0.120, right? And 0.120 is right over here somewhere. And we multiply 0.120 times our electric field, right? This one. So 3,333 times 0.120 gives me negative 399 or negative 400. And it's actually, do they put the negative sign on it in the book? I don't remember. They don't. There should be a negative sign on here for this because that is how the definition of the electric field compared to the potential. But I don't think they tell us that until the next section.
I tried to put the electric field without the negative sign, and it was wrong, but I try now with the negative and it's right.
Okay, good.
Oh.
Yeah, that's so yeah, the negative sign, do you know why it's negative? Do you realize why why the negative sign is there, Georgia?
No.
Okay, the reason that it's negative is because this is the positive direction for X. That's positive X. Electric field always goes from positive towards negative. So our electric field is going in the opposite direction as the positive X direction. So our electric field is a negative electric field. It's negative X direction. So that's why it's negative. Okay?
Yes.
So mine's negative also. I think everybody has the same drawing, so everybody should be negative. When you calculate the potential though, in a uniform field, if E is uniform, in other words, it's the same value in the same direction everywhere. When E is uniform, then this equation is true. V equals, let's see, yeah, E times change in direction. If this is one dimension, it's change in X, or the way that we're doing it, but there's always a negative sign on there. This would be negative V times E times D in this case. So the negative sign is on there. So your voltage changes from the electric field is negative, but the potential difference becomes positive. And the reason for that is when you're going against the electric field towards positive charge things, that increase, that results in a positive potential difference, a positive delta V. If you're going towards the negative stuff, it becomes a negative delta V, or negative potential difference. So that's generally true. And it's a little bit confusing. And again, we have to thank Benjamin Franklin for that. Benjamin Franklin is the one that decided that the electron should have a negative charge and the other charge should have the positive charge. And if he'd chosen the proton to be the negative charge, then we wouldn't have to deal with this negative sign here, but we do. Benjamin Franklin was a genius in many things, but he just chose wrong that particular day. He didn't know any better. How could he possibly know? It was a 50-50 chance. He gambled and lost. He gambled and we lost. Okay, what else is in this problem? Well, so then they want to know the potential energy, right? Well, potential energy from the very first of this chapter is defined because we say that voltage is equal to potential energy of a charge divided by the charge. So potential energy is equal to the charge times the voltage. Since you know the voltage right here, or the potential right here, then you just multiply the charge that's in there. And they said that we're going to put in a charge of plus 550 nanocoulombs. So this is your Q. You multiply it by your voltage here, and you'll get your answer right here. And then they do the same thing here for a negative charge. So just plug in a different Q here times the voltage, and you get a different number here, down here. So now, this last part of the problem, last two parts are a little bit trickier because they're not just calculations. We have to figure out directions and velocities and all this stuff. In this one, they're going to put a charge in between, and you're going to have to calculate the potential energy of the charge, which you've already done because you did it for 0.240 here and here for these two charges. So what you're going to do is you're going to take this potential energy that you have here, and you're going to set it equal to the kinetic energy of the charge. So I'm going to take my potential energy from above for each charge. That's this part for this first one. I'm going to take this number, I'm going to put it right here. And that has to be equal to 1/2 times the mass times the velocity squared. The mass is right here, right? And the velocity is the thing that we're calculating. We want to solve for this. So it ends up being velocity equals square root of u times 2 divided by the mass. Now, I can't remember if they wanted the sign correct up here for you. They do. So whatever sign you get up here, you want to make sure that you don't use the negative. Don't use a negative number in here for your U, because then you'll try to take a square root of a negative number and you'll be confused. But just use whatever, use the absolute value of it to get the absolute value of or magnitude of velocity. Then once you calculate it, once you know the magnitude of velocity, then you just need to draw the picture and calculate which direction it's going to go. So the picture looks like this. The left side is the negative, the right side is the positive. And for the first one, I'm putting a positive charge in. So I'm putting a positive charge like right here. Well, which way is this positive charge going to go?
To the left, right?
You did it again. It's going to the left, right? Whoops, I did this wrong, sorry. So, positive charge is going to want to go this way because the field lines go that way, right? And it's being repelled by the positively charged plate, so that makes sense. So this one is going to go to the left, which is actually a negative value. So your velocity is going to have a negative value here because it's moving to the left. And then a negative charge, of course, will want to move to the right. So it'll have a positive value because it wants to be attracted to the positive plate. So this one will have a positive value. And that, I believe, is what they're expecting here as well. So this one is a negative. This one is a positive. Wow, this one really cooks going that direction.
The bell rang, so.
Okay. Oh, sorry. And this, yeah, so go ahead and go. You're going to have to use some kinematics to get the final velocity, which is what they want to do. But we'll address this again tomorrow, and we'll see you tomorrow. Have a good day. Sorry.
See you.
Thanks.